It is live streamed.
So I think we can start now, right? Okay. Welcome everyone. Welcome to our weekly lecture series of atmosphere dynamics and its applications to climate sciences, which actually started on 18th January 2025, which will be continue up to 2nd August. So today is the 15th lectures. Today the lecture will be delivered by Dr. Somenath Dutta, who is the former scientist of India Met Department and head of Kolkata Meteorological Office. So to start the program, now I would like to request to deliver a welcome address by Professor Dr. Deepak Aryal. He is the member of Education Outreach Committee and a founding member of SAMA from Nepal and member of advisory panel of the current lecture series on atmospheric dynamics. So Professor Deepak Aryal, sir, please.
Okay, good afternoon, everybody. I am Deepak from Kathmandu. Dear respected Professor Ajit Tyagi, Chairman of SAMA, Secretary, Professor Someshwar Das, and Dr. Mohan, and everybody on board. It is my great pleasure to give a small welcome speech on behalf of SAMA and organizing committee. It has maybe the SAMA was started during the peak time of COVID, when we mostly stay in home. At that time, we make some things. Now it has gone a lot. It has done a lot. In the case of capacity building, SAMA is doing very, very well. So in this connection today, as a part of this atmospheric dynamics, part of dynamic meteorology, which is the basic principle to understand the meteorological process in the Earth. We are having Dr. Somenath Dutta as an instructor. He's from IMD Kolkata. I'd like to welcome him too. And he is about teaching about atmospheric waves. From everybody from SAMA's team and the Education Outreach Committee, I'd like to welcome you on board on this class. Thank you. Thank you. Mohan, now it's up to you.
Thank you, Deepak Aryalji, for your nice introduction and welcome speech. Now I'd like to request Dr. Swagata Paira to introduce our today's resource person, Dr. Somnath Datta, sir. Swagata ji, please.
Thank you, Dr. Mohan. It's my great pleasure and honor to introduce a distinguished scientist and educator in the field of meteorology, Dr. Somenath Datta, who currently serves as the head and scientist G at the Regional Meteorological Center, Eastern Region, IMD Kolkata. Dr. Datta is a senior officer of the Government of India, having joined the IMD in 1993 after successfully clearing the UPSC examination and completing his WMO Class 1 training in General Meteorology from the RTC Pune. With over 32 years of service in the IMD, Dr. Datta has contributed immensely to both operational forecasting and meteorological education. He has spent more than 25 years teaching advanced meteorological subjects such as dynamic meteorology, numerical weather prediction, and atmospheric thermodynamics in WMO recognized training program. He also taught NWP to MSc MTech students of Savitribai Phule Pune University from 2022 to 23. Dr. Datta holds a PhD in mathematics from Vidyasagar University. He is also graduated graduation BSc and MSc, BSc from Barwan and MSc from Vidyasagar University with a first class. With his research in PhD, his research focused on computational fluid dynamics and airflow modeling across mountain terrain. He has guided and examined multiple PhD scholars and has authored about 40 research papers in reputed scientific journals. Beyond academia, Dr. Dutta has held important administrative roles, including more than 10 years as the head of the IMD training services at Pune, where he served as a course designer, course manager, and curriculum leader. He has also contributed internationally as a member of the WMO Capacity Development Panel and played a key role in revising the WMO Basic Instrumental Package for meteorologists. Dr. Datta's dedication in operational services, capacity building, this is one of the best part of him, and scientific excellence makes him a truly inspiring figure in Indian meteorology. We are indeed privileged to have him with us today. So it's over to Dr. Mohan.
Thank you, Dr. Shaukat. Now I'd like to request our distinguished speaker, Dr. Somenath Dutta sir, to deliver his talk. Sir, floor is open for you. Sir, please.
Thank you very much. First of all, I wish to express my sincere thanks to our Taggi sir, Somenath sir, and so many my teachers in this group, just like Professor Mohanty, Professor Mohanty, Bhaskar Rao sir, all these things, for entrusting me upon me for designing this course and giving me an opportunity to deliver a few lectures. And I am very much thankful to Professor Swagath for his kind introduction. So now, first of all, I will take the excuse from all the students and audience for excusing me, because I am not very much comfortable in delivering lecture, mainly dynamic meteorology and all this subject using PowerPoint. You may say that I am a very lazy fellow because I could not prepare, and I am habitual of delivering lectures or taking class using board itself. So I will try my level best so that you all will enjoy. And anytime you can stop me. So, so now I am sharing my board. This board is visible, I hope.
Yeah. Yes, sir.
So today's topic is atmospheric waves. We all know very well that that wave may be recognized as a carrier of the physical properties. And due to this recognition, waves in the atmosphere is very, very important, because we all know very well different physical properties. They are having different source regions over the globe. Everywhere they are not source region, but other region also those physical properties are required. So the atmospheric waves, they really does that purpose, that they carry different physical properties like mass, energy, momentum, etc., moisture, from one place to another one place in horizontal as well as vertical direction also. So now regarding atmospheric waves, so many things already has been discussed. For example, for any wave, actually, a certain parameters are very, very important. One is your wave number, which is basically inverse of wavelength. That is, larger the wavelength, smaller will be the wave number. Then another two things also we have heard. That is, one is group velocity. Another one is the phase velocity. As I already mentioned, that wave is a carrier. So now when we consider that wave carrying the momentum, then at what speed the source of momentum is being transported from one point to another one, that is actually phase velocity, phase speed. And in the same way, at what speed energy is being carried by one place to another one place, that is your group velocity. when when we consider a monochromatic wave, then generally in that case your momentum and energy both are propagated with the same speed. So same speed, that means group velocity and phase velocity is same. But when we consider a polychromatic waves, which may differ little bit in their phase and frequency, then in that case actually in that case it is not necessary that always momentum and energy they will be propagated with the same speed. There are some waves, of course, for those cases they are propagated in the same with the same speed, but there are also some waves they are not being propagated. Waves for which the momentum and energies are being transported with the same speed, that means when group velocity and phase velocity are same, such waves we call non-dispersive wave. And when they are not same, then we call dispersive. And you have already seen, actually there is a dispersion relation. Suppose if for a wave, if nu is the frequency, and for a wave, if the k, l, m, these are the wave numbers in the three direction, then a mathematical relation, functional relation between these two, nu and k, l, m, this is known as dispersion relations. If this dispersion relationship is a linear, then we call it, if the dispersion relationship is linear, then in that case, what happened? As another one thing, we from this relation actually three quantities we find out. It can be shown that these three quantities, these are nothing but the different three components of the phase velocity. Three components of the phase velocity. We can denote it by C, and this three quantity, that is del nu del k, then del nu del m, L, and del nu del m, this quantity it is called your group velocity. We generally denote it by Cg. So we can see very well that if this relation is a linear relationship, that means if nu is equal to say ak plus bl plus cm, like that actually, then you can see all these things are same. This is equal to this, this is equal to this, this is equal to this. So naturally then it will be a case of non-dispersive. But if anyone is not linear, then it is a non-dispersive. So all these things you already know in the last lecture. I understand this has been covered. So now here actually in the atmospheric waves, three major waves we will discuss. One is Haurwitz wave, Rossby wave, and then gravity wave. Now for discussion the Rossby wave, one thing I will show. Let us consider the meridional cross section of the Earth. This is your equator. This is a mid latitude. Now let us consider the trajectory of an air parcel initially put at rest at this latitude, and this trajectory, and let us consider its trajectory with the constant. What is that constant? That its absolute vorticity remains conserved. This is constant. Then in that case, suppose if I push this fellow to the north, then after reaching at this point, what type of cyclonic vorticity it will acquire? You can see very well. So suppose my relation is F1 plus zeta 1 is equal to F2 plus zeta 2. So now zeta 1 is nothing but the initial vorticity. As I told initially, the object was at rest. So initially this was is equal to 0. So therefore, zeta 2, this will be is equal to minus F2 minus F1, F2 minus F1. So now when the object has been pushed to the north, so we can understand F2 is greater than F1. F2 is greater than F1. F2 is greater than F1 means, that means zeta 2 is negative. That means if the object is being pushed to the north, then after being displaced to a north latitude, this fellow will acquire some anticyclonic vorticity. So therefore, what will happen? It will turn like this. It will turn like this. Turn like this, it will continue until it will be to the north of this latitude. Then it will come here. Then by inertia, it will cross this latitude. But once it crosses this latitude, then story will be just reverse. Then in that case, following the same logic, you will find this fellow will acquire cyclonic vorticity. So therefore, it will turn like this. In this way, you will get this thing. So, and this is nothing but your Rossby wave. That's why it is told that Rossby wave owes its origin to the conservation of absolute vorticity. As a result of which, the governing equation for studying, for analyzing the Rossby wave is nothing but the conservation of absolute vorticity. That is d dt of zeta plus f is equal to 0. This is equal to 0. This is equal to 0. So now question is already I understand in the previous lecture perturbation technique, perturbation theory has been discussed, and we have already understood through our last lecture the basic purpose of the perturbation technique is to linearize the nonlinear governing equations. So here what we do, we will first of all we will linearize this equation using the perturbation technique. So now we all know, we have learned in the last lecture in the perturbation technique that while applying the perturbation technique, we have to define a mean flow. So here we define the mean flow like this. The mean flow is having only zonal component. Only zonal component. And this zonal component is uniform in the meridional direction as well as in the vertical direction, and we consider the barotropic vorticity equation. Barotropic vorticity equation. The U-bar 0. This is your basic flow, and we have already learned in the perturbation technique that besides defining a basic flow, we need to define an perturbation. So we define the perturbation has two components in the zonal component also, and this also, but if for the simplicity, first let us take there is no vertical. And if I now apply here, so in that case, what should be the zeta? So we can understand zeta will be is equal, zeta you know already, del v del x minus del u del y. So therefore, if from here we can see, so this will be nothing but your del v prime del x minus del u prime del y. What is the physical meaning of that? That means whatever vorticity is there, this is solely due to the perturbation only, which we have just seen. Because after being displacement, when we perturb, after being displaced, what vorticity they are getting. So this is zeta prime. So now if I apply this, all this thing in this equation, then you will get this linearized equation, that is del zeta prime del t plus u bar into del zeta prime del x plus another one thing you will get, that is v prime into del v prime into del f del y. This is nothing but your beta del f del y. This is equal to beta. So this is the perturbation. So now since we are considering some wave, so therefore we will seek a wave-like perturbation. So therefore, so now here actually we define one quantity which we will call perturbation stream function. We will call perturbation stream function. Of course, this is a function of x, y, and t. And if I say this is a perturbation stream function, then automatically I can define that u prime will be is equal to minus del psi prime del y, and v prime is equal to del psi prime del x, because from the definition of the streamline we know all these things. Then accordingly zeta prime, this will be is equal to Laplacian of psi prime. Okay, so therefore all these things, if I substitute in this equation, if I substitute, then what you will get? You will get this one, that is del t plus u bar into u bar del x operated on Laplacian of perturbation stream function, then plus beta into del psi prime del x is equal to 0. Because instead of many perturbation, let there be one perturbation. That's why this is the purpose of introducing this the perturbation stream function. So now we see that perturbation is in the form of a wave. Perturbation is in the form of a wave. Perturbation is form of a, we see that perturbation is equal to a is say psi tilde into e to the power I kx plus ly plus minus nu t. That means we presume that the perturbation is a progressive two-dimensional wave, simply harmonic wave actually. Okay, so now if I apply all these things, actually if I apply all these things, so you can see so how it will. So from here you can see very well that del square psi prime, this will be is equal to your minus a square plus l square into psi prime into psi prime, and then of course e to the power all this thing kx plus ly minus nu t, this thing. So therefore if I apply all these things, then what you will get? You can see very well, you will get minus I nu plus u bar ik into psi tilde. Of course, this minus k square plus l square will be there. Minus k square plus l square will be there. This, then plus beta into beta into ik, correct, into psi tilde. This is equal to 0. This is, and from here you can straight away get this relation that nu is equal to u bar k minus beta k divided by k square plus l square. So ultimately you got the phase relationship. So from this phase relationship you can understand very well that this is not at all a linear relation, isn't it, between nu and kln. So therefore from here itself we can say that Rossby wave is not at all a non-dispersive wave, rather it is a dispersive. And from here you can find out what is C and what is CGK. What is CGK, you can find out. So you can see from here you can find out that C is equal to nu bar by k nu bar by k, Cx rather, let us say, this will be is equal to how much you are getting, u bar minus beta by k square plus L square. So from here, another one thing we can see, it is a good thing that you can see very well. If I consider the Rossby wave embedded in a westerly mean flow u bar, then you can see that Cx is less than u bar. So what I can say, that Rossby wave retrogrades in a westerly mean flow. Retrogrades means what happened? That means this Rossby wave is moving at a lesser speed than the mean flow. This you can see. And at the same time, you can also find out CGX also. CGX also you can find out. For the time being, for the simplicity, if you don't consider L square, then you can see you will get u bar plus beta. If you don't consider L, beta by k square. So here you can see that group velocity is more than u bar, So what we can see, that with respect to an westerly mean flow, the group velocity is progressive, but the phase velocity is not phase velocity is not moving forward. It is moving back. So it can be interpreted in a different way, because we all know very well that direction of the propagation of any physical property by the wave is always from the source to some other point. So now, if I consider the momentum, source of the momentum is the mean flow only. So therefore, speed of transportation of the momentum cannot be more than the mean flow. But if I consider the energy, here energy is nothing but the wave energy, disturbance energy. Wave is the source of the disturbance. So therefore, here you can see that group velocity is more than this. So this is about your Rossby. Now we will see the Haurwitz wave. In the Rossby wave, actually there are a lot of simplification we have made, which are not at all realistic. You can see we have seen Rossby wave. We have taken mean flow is just u bar. It is neither a function of z and y. Okay, we are not taking it is a function of z. It is fine, horizontal, but definitely Rossby in the atmosphere, whatever we see, that does vary with y. So now we consider the mean flow, where we consider the mean flow. Of course, it is having only one component, that is this one only, and that is your another two component 0 0, and remaining treatment is same only. But thing is, someone has raised some question. Yes, Mr. Juheb Kabir, shall we discuss the question now, or we should discuss the question later?
We can discuss in later phase.
Later. Okay.
Yes.
Okay, fine then, fine. So so in case of Haurwitz wave is nothing but a generalization of Rossby. We will see generalization of the Rossby. Here actually we take this one, and governing equation is same. Governing equation same means it is the same governing equation, del zeta del t plus u bar into del zeta del x. It is same only, and sorry, not u into del zeta del x plus v into beta. This is equal to 0. Governing equation is same. But thing is, here actually mean flow is this one. Just a minute, I think I made a mistake here. It is not only beta, it should be v into beta minus del u bar del y also. Del u bar del y also. This is equal to 0. This is equal to 0. So here also it is the same technique we apply. That is your perturbation is having it has a perturbation. Now perturbation, there are the perturbation is like this. Only thing is, you remember here also we will introduce the same stream function also, that same stream function, so that v prime will be is equal to del psi prime del x, and u prime will be is equal to minus del psi prime del y, same thing only. And we will get the equation like this. We will get the equation like this, that is del t plus u bar into del x of this one, and then you will get, that is del psi prime del x within bracket beta minus del u bar del y, beta minus del u bar del y. This is equal to 0. You will get this equation. And only thing is, here psi prime we will take like this. You remember there actually amplitude was not at all a function of anything. Here we will take amplitude is a function of y, and the phase is only, it is a function of x and t, that is kx minus nu t, this one. And there is one condition is there, that psi tilde plus minus d, this is equal to 0. That means this Haurwitz wave decays in the meridional direction after traveling this much, after traveling d on both, and this is the reference latitude actually. Okay, so now using this, ultimately you will get a phase relationship. That phase relationship is equal to, phase relation we will get, just a minute. Phase relation we will get, yeah, you will get the phase relation, that is u bar k then u bar k minus k within bracket beta minus d2 u bar dy2 divided by k square plus pi square by d square. Yeah, pi square by d square. You will get this relation. Now, this is the phase relation for the Haurwitz wave you will get. So now, if why I told that Haurwitz wave is a generalization of the Rossby wave, because now if you put the Rossby wave condition, that is Rossby wave told that mean flow is uniform in the meridional direction. If it is so, then this will be equal to 0. And if the mean flow is uniform in the meridional direction, then at what distance in the meridional direction this mean flow will be equal to 0? That perturbation magnitude will be 0. This must be an infinite. So therefore, in that case, d will be very, very large, infinite. So this will be equal to 0. And ultimately, you will get the phase relationship of the Rossby wave. So that's why Haurwitz wave is the generalization of the Rossby wave. And as such, in the atmosphere, whatever Rossby wave we see, they are basically all Haurwitz wave, because the mean flow is, of course, is a function of y. So this is about Haurwitz wave and Rossby. Now let us come to gravity wave. We all know very well, for any wave to be excited, we need one disturbing force and another one is your restoring force. We all know very well. Now, disturbing force may be anything. It may be your isolated heating, it may be orographic lifting, so many things may be there. But for gravity waves are a special types of waves where the restoring force is the buoyancy. Restoring force is the buoyancy, which we call effective gravity. Buoyancy. It is nothing but G into rho minus rho prime divided by rho. So actually what happened, so suppose if I consider an air parcel emerged in the ocean of air, so then in that case, actually what happened, this fellow will replace some amount of atmospheric air, that is ambient air. Now density of the ambient air, it may be rho, and density of the air inside this air parcel, it may be rho prime. So now question is, so then in that case, this fellow will be exerted upon by two forces. One is by its own weight. Another one, it is the force exerted by the displaced amount of air actually. So therefore, net force per unit mass, this is actually this one. It can be this, and this we call effective gravity. So gravity wave. Now broadly, gravity wave we can divide into two parts. One is your external gravity wave. Another one is your internal gravity wave. External gravity wave is like this, where the horizontal length scale is about 1000 kilometers. It is a large scale, and vertical length scale is about 10 kilometers. And even if I don't want to specify, I can say that horizontal length scale is much greater than the vertical length scale. And another one thing is all that external gravity wave can propagate along the free surface, but it cannot propagate vertically. This is not allowed. But in case of internal gravity wave, here L and H both are same, that is of the order of 10 kilometer only. And here both the things are allowed. This is also allowed, and this is also allowed. Both the things are allowed. This is your internal gravity wave. Okay, so now slowly now first let us consider the external gravity. So for external gravity, we will take the simple very simplified example of shallow water gravity wave. In case of shallow water gravity wave, what we do, we consider one type of fluid, say density rho1, and above that there is another one type of fluid is there, that is rho2. So it is that interface. So unless being disturbed, interface looks like a plane. It is a plane surface only. But now you can disturb it. How you can suppose this is this you can move. Just you move this one and you leave it. Then in that case, this interface can no longer remain just like a plane surface. Then interface looks like a wave, and this is nothing but your external gravity wave. Now to understand or to get the dispersion relation of the external gravity wave, we consider two-dimensional motion, x and z, two-dimensional motion, and for that only we take two governing equation. One is your u momentum equation, another one is a continuity equation. So u momentum equation, it is like this actually, that is your du dt is equal to minus, now this is your rho1. Of course rho1 is greater than rho2. This is equal to minus 1 by rho1 into del p del x, and another one equation we take, that is your, of course, frictionless flow we take, frictionless flow, and it is non-rotational, it is not rotating. Okay, frictionless flow, And another one equation we take, that is a continuity equation, that is del u del x plus del w del z. This is equal to 0. Del w del z is equal to 0. Now to find out the pressure gradient force, what we do, we take one point on the wave and another one point here, another one point here, okay, another one point here. And suppose if this point pressure is let's say P2 and if this point pressure is P1, then del P del X and del P del X is approximately is equal to pressure at this point minus pressure at this point divided by this one. And it can be shown, I have already provided it, that minus this will be is equal to minus 1 by rho 1 into rho 1 minus rho 2, rho 1 minus rho 2 into rho 1 minus rho 2, just a minute, into G, yeah, into del H del X into del H del X. Now question is, what is H? H is nothing but height. This height, these are all H. These are all H. This is variable. These are all H. These are all H. Okay, del H del X. And this we can find out. And how it can be done? This point pressure minus this point pressure. And this point pressure we can find out. This is nothing but the weight of the air, this air column. Okay, and this point pressure, weight of this air column. So this will be definitely some point you have to take pressure up to this. Up here, pressure up to this, then weight of this column. Okay, so basically this del P difference of the pressure will be nothing but weight of this air column minus weight of this fluid column only. But you remember, this air column is having the density rho 2 and this air column having the density rho 1, and this is equal to delta H. Okay, and this is equal to delta X. Okay, delta X, and it can be shown that this is equal to this one. And now let us see one thing. Now this rho 1 and rho 2, whatever we see, this rho 1, this is also not varying with height, and rho 2 also not varying. These two are constant, even though different layer having different density, but this rho 1 is a constant quantity, rho 2 is also a constant quantity. As a result of which, right hand side is an independent function of Z. It is not dependent on Z. As a result of which, this du dt will be is equal to then del u del t plus u del u del x, There was another one term, that was a w into del u del z. This term will no longer remain because of that logic which I told you, that right hand side is independent of z, so left hand side has to be independent of z because it is a differential equation. So this is one governing equation, and another one governing equation, how I will get? Now this equation I have to integrate it from z is equal to 0 to an arbitrary value, z is equal to h. If I integrate, then what I will get? You will get h into del u del x, and here you will get w at h minus w at 0, and this is equal to 0. W is nothing but vertical velocity. Vertical velocity at z is equal to 0. We take it is equal to 0 only. That is this one, this bed, ocean bed. This is 0. This is 0. And w at h, this is equal to, because this vertical velocity, this is due to the change in h. Change in h due to the flow in the along the x direction, that is del h del t plus u into del h del x, u into del h del x. So therefore you get another one equation, that is del h del t plus u del h del x del H del X, and then another one your H into del U del X is equal to 0. This is one equation you are getting. So these are the two governing equation. Now in these two governing equation, you can say this is 3, this was 2. In this two governing equation, again we will apply the perturbation technique. So perturbation technique, let us apply. If I apply the perturbation technique, then we will put U is equal to U bar. Here for simplicity we take the mean flow is having only zonal component. This is also independent, this is also constant, and one part and another perturbation is a function of x and t only. That means it is moving with time and in the along x direction, and h is equal to, that is h is, you can understand this height, this height, this height, h is equal to your mean height plus h prime into h prime xt. So now all this thing, if I apply if I apply, then what I will get? You will get del t plus u bar del x, u bar del x of u prime is equal to is equal to your g into is equal to minus g into rho 1 minus rho 2 divided by rho 1 into del h prime del x. This one you get, and another one equation what you will get? Another one equation you will get del t plus u bar del x of h prime plus you will get linearization. If I do the linear, del h u prime x is equal to 0. H is equal to 0. So now I have to eliminate. You have to eliminate your u prime. So if I want to eliminate u prime, this equation you do, you make the operation h del x. So let us do h del x. If I do, so here it will be h del x, and here you do del t. You operate another one, that is del t plus u bar into del x whole square. So if I do, so you do this one, and here it will be what? That is your del t plus u bar del x of h prime. This is equal to 0. So now you subtract. If you subtract, then this will be cancelled. Then ultimately you will get the equation, that is del t plus u bar into del x operated twice on h prime. This is equal to g into capital H, minus minus will be cancelled, into delta rho by rho 1 into del 2 h prime del x. You can see this is a typical wave equation. So let us seek for a wave solution. Let us seek. So h prime is equal to, let us say, h tilde into e to the power I into kx minus mu t. So if I apply all this thing here, you will get this. You can do. You will get nu is equal to u bar k plus minus under root g into capital H into delta rho by rho 1. Okay, and from here you can see C or CG both, and into K, C and CG both will be same. This will be is equal to u bar plus or minus under root G capital H into delta rho by rho 1. This U bar has a name. This is called Doppler shift. This is called Doppler shift, and this is called shallow water gravity wave speed. Shallow water gravity wave speed. Now, if I consider our atmosphere, in the atmosphere, what happened? Our below fluid is nothing but your water, isn't it? Ocean water, and above is your air. So now we know very well that is air density is much smaller than the your water density. That means rho1 is much larger than rho2. As a result of which your delta rho is almost equal to rho1. So as a result of which C or Cg, it becomes is equal to U bar plus or minus under root small g into capital H. This is gravity wave speed, and this is U bar is the Doppler shift. So this is the external gravity wave. So we can see external gravity wave is also your what is called non-dispersive wave. Example, very nice example of external gravity wave. The tsunami is also an example of external gravity wave. So sometimes in our advanced course, this type of question comes that if you take the mean ocean depth is 4 kilometer, I think. If I am wrong, I may be corrected kindly. Mean ocean depth is almost about 4 kilometer. So therefore, what will be the gravity wave speed? You can calculate very well. 4 kilometer, you will find it comes about 200 meter per second. Almost it comes about 200 meter per second. So this is your external gravity wave, and this gravity wave can transport the physical properties from one place to another one place in the horizontal direction, but not in the vertical direction. Now we will go for the internal gravity wave. For studying the internal gravity wave, we consider a very simple assumption that there is no mean that we consider on again we consider two-dimensional flow only, that is in the XZ plane. And since the scale of the motion is very small, you can say understand it is a non-rotational. Actually, effect of the Coriolis force will be very small. It will almost not there. So therefore, your all what are the equation you have to take? You have to take the U momentum equation. That means del U del T plus U del U del X, and this is equal to, and here another one assumption we take, internal gravity. Actually, that is a Bushnell's approximation. In internal gravity wave, we take one assumption that is called Bushnell's approximation. According to this Bushnell's approximation, density is treated everywhere constant in the governing equations, except in the vertical momentum equation where it is coupled with buoyancy. Okay, so therefore in the horizontal momentum equation, of course we will use the constant density. That constant density is nothing but the density, mean density of that particular level, and then del P del X, of course, and other forces are not. We consider a frictionless, adiabatic, non-rotational flow. This one, and another one equation, this will be your del W del T plus U into del W del X, and here actually two forces will be there. One will be your G into theta by theta 0, theta by theta 0, G into theta by theta 0, and another one will be minus 1 by rho into del P del Z, and continuity equation also we have to take, that is your del U del X plus del W del Z. This is equal to 0, and another one is your adiabatic equation, that is d theta dt is equal to 0. So this will be equal to del theta del T plus theta is potential temperature, that is U del theta del X plus W into d theta dz. This is equal to 0. So anyhow, these are your governing equation, and on this governing equation again you apply the perturbation technique, get the linearized equation, and in the linearized equation again you apply the wave-like approximation, and then what you will get the expression for the dispersive wave. So that you can do this, you will get this is equal to nu is equal to u bar k minus, just a minute, let me just a minute. Yeah, this you will get u bar k, yeah, nk divided by k square plus m square. So you may ask me that what is this suddenly, where from this k and m has come? Because that perturbation, any perturbation we have taken like this, that amplitude into e to the power I ax, that means it is propagating along the x direction and vertical direction, mz minus nu t. Okay, nu is the frequency, k is the wave number in along x axis, m is the wave number along y axis, z axis. Okay, and this n is nothing but Brand-Weissala frequency. N is equal to under root g by theta bar into d theta bar dz. This is nothing but Brand-Weissala frequency. Brand-Weissala frequency, sometimes we call it buoyancy frequency also. Okay. Achha. Oh, sorry. Actually, it is not only minus, it is actually plus minus. Yeah, it is plus minus, and here it is not k square plus m square, it is k square plus m square to the power half. Again, you can see that it is a non-linear relation. So therefore, from the relation itself, we can understand it is a dispersive wave only. So now what happened, we will consider the vertical component of the internal gravity wave for a special case. For simplicity, let us take u bar is not equal to 0, u bar is equal to 0, So then in that case, Cz, this is nothing but your nu by m, isn't it? Nu by m. How much it will be? It will be plus or minus capital N into k m and then k square plus m square. K square plus, and Cgz, this is your del nu del m. What you will get, you will get minus, within bracket again, plus minus, if I am not wrong, it will be nkm then k square plus m square to the power 3 by 2. You can find out it. So now, one very interesting feature is that this I am leaving it to my dear students, that you can do one thing. Here you put k, different sign of k, plus, minus, and here you put different sign of m, plus and minus, and then you will get this sector. Now you find out what is the sign of Cz and what is the sign of Cgz, and you will find in all cases they are opposite to each other. This is an unique property of internal gravity wave, that direction of vertical phase propagation is different, opposite to the direction of the vertical energy propagation. So therefore, if I consider an internal gravity wave, which is vertically propagating internal gravity wave, then in that case, what happened, in that, another one important thing is there, that this I should say, this quantity actually known as, this is has another one name is there, intrinsic frequency. This is called intrinsic frequency of internal gravity wave. Okay, So now, if the intrinsic frequency becomes zero, for my point, it is a true for any wave actually. For any wave, if the intrinsic frequency vanishes, then that wave breaks down. And now intrinsic frequency everywhere it cannot be. Now question is, let us consider your internal gravity wave. Okay, internal gravity wave, and it is like that. The momentum is propagated downwards, energy is propagated upward. That's just now we have seen. So now, if the momentum is being propagated downwards continuously, then what happens? After some time, a situation may arise when the intrinsic frequency becomes very, very smaller, it may vanish, and then the internal gravity waves breaks down. And when internal gravity waves breaks down, then what happens? Whatever energy it is carrying, where it breaks down, it just give it to that particular level, to the mean flow at that particular level, and suddenly that mean flow at that level becomes a very great source of energy, and that is being demonstrated in terms of some turbulence. That's why many times it is also believed that for the clear air turbulence, vertical propagation of energy, I mean, this mechanism, whatever I told you, by internal gravity wave, it also plays an important role. And hence I finished today. Thank you very much.
Thank you, Dr. Somenath Dutta sir, for your nice talk and very insightful talk. So, Deepa, we can go for the photo session, right?
Yeah, yes, sir. Yes, sir.
Okay. So now I'd like to request everyone, please switch on your video so you can make a photo session. Tyagi sir, please. Mrunal
Questions? Some
and Rohini, please. So, Mrunal, you can take a
Sir, after the
screenshot.
photo session, we can
Yeah,
have
please.
the question answer.
Okay, ready? 3, 1 minute. Okay, I should make it full screen. Okay, ready? 3, 2, 1. Click. Thank you. So now time for Q&A session. So I would like to request Dr. Deepa. Are you ready? So
Yes,
you
sir.
can
Yes, sir.
conduct the Q&A session.
Yeah.
Please.
So actually, in the question answer session, question answer, there is no question. Still, there is no question. So I am requesting to all participants, if you have any question, then please write in question.
Dr. Divya, there is one question from Farnu Shahad. Just now it has come.
So someone raised hands, I saw. Ajay.
Should I read?
Okay. Yeah. So there's a one question from Farnus Haddad. Thank you so much for this lecture, where we can see gravity wave in the atmosphere.
Oh, in the atmosphere, there are many gravity waves actually. For example, mountain wave. We all know mountain. When air flow passes across a mountain, that time also gravity wave, mountain waves. It is an example of internal gravity wave. Even thunderstorm, in case of thunderstorm, that is also actually internal gravity waves can be generated by many disturbance. One is convective heating, isolated heating, then your orographic lifting. Internal gravity, many there are actually. Actually, it is very small scale. I told you, 10 kilo of the order of magnitude is horizontal scale is 10 kilometer. Many, there are many. Even I am telling you, clear air turbulence. When we fly, that time that whatever clear air turbulence, that is due to there is the effect of the, to some extent, it is the effect of the internal gravity wave actually. I am very sorry. Actually, I am not habituated to finish so quickly. It takes time because I skip so many derivations also. and all this thing due to the because I would like to show the participant how the derivation, how the result comes actually, so that through the class people will learn the mathematical techniques also, how it is being done. So but anyhow I could not do because time is very short within this. Generally, you know, Haurwitz wave and Rossby wave, I takes one class, 1 hour 15 minutes. Then external gravity wave, internal gravity wave, another one class or 1.5 classes. Anyhow, there are a lot of times are there allotted in generally in a regular course, but here times are not there. So anyhow, even later on also, if there are any, because material I have already shared after reading the material, if any student is having any question, any doubt, so I will be very happy to share my view. Thank you very much. Any
Thank
other?
you so much, sir. So, if still if any participant have any question, then please write your question.
Already there is one.
Yeah, sir, there is one more question. What are the physical application and significance of the Brunt Besala frequency? Brunt Besala frequency, yeah.
Sir, you're
Sir,
muted.
mute, yeah.
This brand actually now, instead of brand Vaisala frequency, we take the square of the brand Vaisala frequency, that is g by theta into d theta dj. This is nothing but a measure of atmospheric static stability. If this is positive, that means atmosphere is stably stratified. In that case, we can't expect any convective development by its own. And if it is negative, then only then it is atmosphere is convectively unstable. It is very, very important actually for operational forecaster on a regular basis. They look at it, that whether the local atmosphere is convectively stable or not. Even not only that, they used to see the forecast value of n square also. Am I correct, Somenath sir? Because you are a great modeler. Forecast value of also n square. That is, for example, I am working in an airport. For example, I am working at an airport. Okay, I would very much know that that whether around my airport, whether there is any possibility of convective development. Immediate thing is using the radio sonde data, find out the vertical profile of this is the digit. And main thing is, if you plot n square versus z, you will be able to find out the layer where which one is convectively unstable. It has a lot of practical application. Even I may be, whatever I told, it may be very, very less. There may be many. Even in a planetary boundary layer, whether the flow will be laminar or turbulent, that also depends broad to a major extent on this, along with of course winds there. I hope my question has.
Sir, thank you. And sir, there is a one very special request to you from Dr. M. Kalyani. Please take another class. The participant is very interested after attending your class. But there is a one question: how the internal waves influence ocean mixing in vertical?
Because internal gravity wave has a property, that is it propagates vertically. So now if an wave carrying chithi, money order, etc. They are actually carrying the physical property. So when it is moving vertically, so naturally, from one layer to another one, there will be transport of physical properties. Physical properties, it is a generic term I am using. Any physical properties, mass, energy, salinity, etc., etc., etc. In the ocean, it plays a very important role. I hope I have clarified the.
Yes, sir. So, thank you so much for giving for the taking all the questions. Thank you so much, sir. Now over to you, Mohan sir.
No, there are
Thank
other
you, Dr.
questions
Deepa,
also.
for your nicely conducting the.
More,
Yeah,
more.
Shagataji,
Okay,
please.
one more
Yeah.
question. Yeah, one more
There
question
are
is there.
few
Yeah.
more questions also.
So, one is cyclone mixing, internal wave mixing, what scales they influence?
Pardon, sir, I am not getting the question.
Sir, there is one question. Cyclone mixing, internal wave mixing, what scales they influence?
Cyclone mixing.
Yeah.
Cyclone mixing.
Sir, I think it is the previous question's continuation. How the internal waves influence ocean mixing in vertical,
Okay.
cyclone mixing, internal wave mixing, and how which scales they influence.
Yeah,
It's a
yeah.
connected one.
Okay.
And one more question is how Rossby waves at mid latitude different from that at tropics?
Okay. Actually, what happened, from the what is called intuitive analysis of the Rossby wave, which I initially showed, you can see that Rossby wave generates there where there is a significant change in the sign of F. This we have to remember. Rossby waves generates there where there is a significant difference of sign of F is there. Now try to understand that the globe we can divide into three belts. One is equatorial belt, one is tropical belt, another one is mid latitude. So now question is, in the mid latitude belt there is a significant change in F actually. Correct? Because from 30 degree to we goes to 45 degree, and another one we are getting at the equatorial. Tropical Rossby wave actually generally it is not equatorial Rossby wave there, which we will discuss in the next class. I think in the next class we will discuss.
So, question there
Another
is
one
one.
thing, Rossby wave is also known as long wave. Rossby wave, long wave actually, it is also known as long waves in the western. It plays a very important role. Just like our westerly waves during winter season, all these things we say. This you can also say Rossby wave actually. These are nothing but the long waves in the western. And Rossby wave also there are many. Yeah, another one thing I will take 2-3 minutes time. That is sometimes you may get a stationary Rossby wave. Okay, depending on depending on the mean flow and the latitudinal belt. For every latitudinal belt, for a given mean flow, you can find the critical length of that Rossby wave, length of which is stationary, and this is in our dynamic meteorology it is known as critical wavelength, critical Rossby wavelength. And generally it is seen, I could not get time. One day if I get time, I will give my own personal time, that it can be shown that if any Rossby wave whose wavelength is greater than this critical Rossby wave, they are retrograde. And the Rossby wave whose wavelength is lesser than the critical Rossby wavelength, they are progressive. And it has been seen about 6,000, 10,000 kilometer wavelength, they are retrograde actually. These are treated as the long wave. At 3,000 kilometer like that, they are progressive. They are treated as a shorter size of the Rossby wave. And very nicely analytically it can be seen also.
Okay, thank you, sir. So now there is no question.
So all the questions are covered, right?
Yeah, yes, sir. Yes, sir.
Yeah.
So
Thank you. Thank you, sir, for your very fascinating lectures and very positively response all the questions. Now it is time for vote of thanks. Now I'd like to request Ms. Muran Naik to deliver a vote of thanks.
Yes, thank you, sir. Just a second, I will share my screen.
नहीं हो तो थोड़ी देर बंद कर अरे बंद क्यों बिल्कुल
Yes, on behalf of organizing committee, I would like to express my heartfelt gratitude to each of you for your contribution on this 15th lecture of weekly online series on atmospheric dynamics and its application to climate science. Firstly and foremost, I extend my sincere thanks to Professor Deepak Arya for his warm welcome address and for sharing a brief overview of this lecture series. My deepest appreciation goes to the speaker of a day, Dr. Somenath Dutta sir from IMD Kolkata, for delivering a very informative lecture on atmospheric wave. Today's session was particularly special as it is marked the first lecture in the series delivered using a digital whiteboard, creating an interactive classroom-like experience for all attenders. I would also like to thank Dr. Mohan Kumar Das for moderating today's session and Dr. Divya Prakash for managing the question and answer session. Special thanks to all our panelists and EC members for their guidance and constant support for every minor detail. I also extend my thanks to all participants and attenders who joined us from across the globe. Last but not the least, a heartfelt thanks goes to team member of Savitribai Phule Pune University for their dedication behind the scenes efforts in successfully organizing this session. Thank you so much, sir.
Thanks also goes to
you.
Dr. Swagata for introducing our speaker, today's speaker.
Yes.
And thanks to Minal also.
Yes, of course. So I will just like to share today's statistics. So around 133 participants have recorded their attendance, and 117 participants have rated it as excellent or very good. The excellents are more compared to very good. So very nice, sir. Thank you so much.
Thank you very much for giving me an opportunity. So, if it is over, then with the kind permission of the chairman.
Well, it was really a great, fascinating lecture today. In fact, for the first time in the entire lecture series that someone has used an electronic board to explain the equations, the intricate equations to the students. And I can see by the attendance that even till the last moment, almost 80 participants were attending your lecture live. Otherwise, what happens is that initially people come, they will just sign the attendance sheet and then many of them just vanish away. But in today's lecture, I see that people are continuously present in a lecture. And also people are requesting that you please give another lecture. In fact, for those who are not aware, let me say that Dr. Datta will give 6 lecture continuously, one after another. So please be attentive and attend all his lectures. All his lectures will be equally interesting and equally good. Okay. So thank you very much once again, Dr. Datta, for very, very fascinating lecture. Thank you.
Thank you. Actually, sir, I belongs to the old generation person.
This is the way.
I don't belong to the new generation, digital generation. But anyhow, this digital boards, now I have tried to make it use. That is during COVID period actually. So during COVID period, we have learned many things actually. Of course, COVID is very bad. There is no doubt. But anyhow, Majburi ka naam Gandhi ji.
No, it was quite good. Maybe Dr. Professor Tyagi Saab would like to.
Yeah, Somenath old is gold, and it's a new flavor to our lecture series. And no doubt, in fact, I felt so good you writing on the screen and relating, and you had time for explaining each of the equation or line you wrote with the physical meaning behind it. So that is very important part, and the topics which you are going to cover are very important. They form the basis of the atmospheric dynamics application part of it. So the great, and we are really thankful to you for planning these atmospheric science dynamics program and also delivering lectures. So we are really thankful from SAMA side, or each one of us. Thank you, and look forward for your.
Solicit your blessings only, sir.
No.
You are just Bhismo Pitamaha to us. I just only solicit your blessings. No appreciation.
No, 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 no.
Appreciation may make me over complacent. That is a dangerous thing.
No, no. See, the hardcore teachers are never complacent. It's only the one of us like us have to give one odd lecture somewhere, then you get appreciation, you become overconfident. But as a teacher, he's always trying to give best to the students, and so thank you so much.
So, sir, with your kind permission, can I leave the meeting, sir, now?
Yeah, please do that.
Thank you very much.
Thank you.
Participants are requested to stay. There is another short program. So it will be interesting. You would also like to be a part of it.
I think
Yes, Dr. Rohini. So we can request every members to join as a panel member. So please, you are already the host.
I will make
Yeah.
you host, and you
So-
can select them, right?
No, everyone. You just
Acha,
make it
everyone I can-
whatever.
So, sir, can we stop the live recording?
Oh, yeah.
Live streaming.
Yeah, please stop live streaming.
Yeah, we can stop, but we can record the program, right?
Yeah, recording will be continuing. Live streaming will be
Yes.
stopped.
But
Okay.
prize distribution, what is the problem?
You want live streaming?
So